So 6.2, we're going to learn about the natural base. So again, this kind of ties in with what we've been doing with our exponents and everything. The natural base e is what we're focusing on. So this natural base, it's a button in our calculator. It's kind of like pi, but I guess the less popular version of pi. It's all you really need to know is that it is a button in our calculator, and it deals with exponents because as our exponent here gets bigger, as our x's here approach infinity, you get closer to e. So e is really just a button in your calculator. Nothing super special about it. So we're going to simplify each expression. So we use the same properties that we learned with exponents here. It's just our base is e. But our base is the same for each of these, so we can combine them. We're multiplying, so how do we combine these two together? Add the exponents. So it's the same thing as saying like x to the third power times x to the sixth power. Same thing, the only difference is x is e. So we have e to the 3 plus 6 power, which is e to the 9th power. So we just add them. What do we do when we're dividing? Subtract them. So first we just want to deal with our coefficients out here. Can we simplify 16 over 4? What does it simplify to? 4 over 1, or just 4. And then we have e to the power of 5 minus 4. What's 5 minus 4? 1. Do we have to write the 1 there? Nope. So we just have 4e. And then example C, what do we do here?
Square.
We have to distribute that 2 to both things here. So 3 and e to the power of negative 4x are being multiplied to each other. So this is being multiplied to this. So we have to make sure we distribute that 2, so it's 3 squared times e to the power of negative 4x squared. So don't forget, you have to square the 3 also. So what's 3 squared? 9. And then how do we simplify e to the power of negative 4x squared? What do we do when we have a power raised to a power?
Would it be like e to the negative 8?
Awesome. We multiply these. So it would be e to the power 2 times negative 4 would be negative 8x. Nine is the numerator. And then what do we do with e to the power of negative 8x? Where does it go?
Put it under.
Put it on bottom. And it becomes positive. So this is just our simplified answer. That was an accident. Is this what you're talking about? All right, 3 more, just like the ones we did before. What do we do here? Add the exponents. Since we're multiplying, we add the exponents to combine. So what is 7 plus 4? 11. So e to the power of 11. What about for number 2? Can we simplify our coefficients? What's 24 over 8 simplified to? 3. And then what do we do with our e's? Subtract them. So e to the power of 8 minus 5. What's 8 minus 5? So 3e cubed. Okay, next. What do we do here? Distribute the cube to both things on the inside, so it's 10 cubed and times e to the power of negative 3x cubed. So what's 10 cubed?
1,000.
1,000, perfect. And then what's e to the power of negative 3x cubed? How do we...
27. Or e negative 27, right?
Remember, we just multiply these. So when you have a power raised to a power, you multiply them together. So it'd be e to the power of negative 9x. What do we do if we have a negative exponent?
You put it under 1.
Put it under 1, but we have a number on top to put it under. So what would go on top here?
1.
What happens to that 1,000? Does that have a negative exponent? No, so the 1,000 stays on top. And then just the only thing that has a negative exponent moves to the bottom. So the e to the power of 9x would go on the bottom. And it becomes positive when you bring it to the bottom. Alright, so our natural base functions also have graphs that go along with them. They're super similar to our exponential graphs that we did in 6.1. However, instead of having a number as our base, we have e as the base. So when we have a positive x, our graph looks like this, and it has exponential growth. So when our x is positive, we have exponential growth. When our x is negative, we have exponential decay. And remember from 6.1, usually if our base was greater than 1, we had growth. And if our base was less than 1, we had decay. So here, this negative exponent is actually making this 1 over e to the x. So it's changing our base to be a fraction. So that's what makes this less than 1 and what makes this decay. So when you have a negative exponent, it changes it to a fraction, which means we have decay. All right, so example 2, tell whether each function represents exponential growth or exponential decay. Do we have growth or decay here?
Growth.
Growth. Because our x is positive, we have growth. What about for b?
Decay.
Decay. And then just as a reminder, if we have growth, our graph looks like this. If we're decaying, our graph goes down like this. So same thing as our exponential functions from 6.1. So for 4, do we have exponential growth or exponential decay? Is our x positive or negative? Positive. So we have growth. So that 1/2 isn't the thing that has the exponent, so it just gets multiplied at the end, so that's not really what we're looking at. The 1/2 doesn't even matter here. We're just looking at the e to the x. The x is positive, so we have growth. So our graph would be increasing like this. What about for number 5? Decay. Since our x is negative, we have decay. That means our graph decreases. And number 6.
Growth.
Awesome. We have growth. So our graph goes like this. Any questions here? So in 6.1, we had our compounded interest formula. In 6.2, we have continuously compounded interest, which is a different formula. So anytime you see the word continuously, you have to use a different formula than what we use for our compounded interest. So this was our formula for 6.1. If it is continuously compounded, we have to use this formula. I call it the PERT formula because it's A is equal to P times E to the power of RT. And these stand for the same thing that we did in 6.1. So A is our amount, usually what we're trying to find. P is our principal, or starting amount, same thing. E is just that button in our calculator, so E is always going to be E. It's not a value that we plug in, it's just that button that you click in the calculator. R is our rate, always in the decimal form, and T is time. So the only thing that makes this different than what we did in 6.1 is if the problem says it is continuously compounded, we have to use our PERT formula. So example 3. You and your friend each have accounts that earn annual interest compounded continuously. Continuously means we're going to use our PERT formula. The balance A in dollars of your account after T years can be modeled by, oh look, it gave us the formula. The graph shows the balance of your friend's account over time. Which account has a greater principal, which has a greater balance after 10 years? So I forgot to include the graph. Silly me. But let's find the balance after 10 years. So where's 10 going to go in our formula? In time. So we have A is equal to 4,500. So that was our starting amount. Our rate would be 4%. So 0.04 times 10. And then we're just putting this into our calculator. Remember, you have to follow your order of operations, so you need to follow PEMDAS. Please excuse my dear Aunt Sally. Got to follow your order of operations or else you're not going to get the right answer. So what would we do first here in our calculator? Right, we got to multiply these together first and then treat it as an exponent. So what is 10 times 0.04? 0.4. So this is 4,500 times e to the power of 0.4. What do we do in our calculator next? Awesome. We click that E button, and our exponent is 0.4. So we have 4,500 times, and I got 1.4918. So if you can, keep it all on your calculator when you're doing it, just so you don't round and lose some exactness to your answer. And then we multiply these two together. So what do you guys get? Anybody do it? Perfect. 6,713.21. And since we're dealing with money, we just round to 2 decimal places. So anytime you're dealing with money, you always want to round to 2 decimal places because we're just talking about cents. So it's an actual like E button in your calculator. So in my calculator, I have like E raised to the power of X, like that's the button that I click. And then it like goes E with the little caret, and then I put the 0.4. So it's like E raised to the power of 0.4. And then I find this value, which is here, and I multiply it together to the 4,500. So that 0.4 is your exponent, so just make sure you have that E to that power. So make sure you guys know how to use your calculator. Super important. All right, next we deposit $4,250 in an account that earns 5% annual interest compounded continuously. So it says continuously, means we're going to use our PERT formula. Compare the balance after 10 years with the accounts in example 3. So here we need to come up with our formula. So we have P is equal to, A is equal to P times E to the power of RT. So A is the amount we're looking for. What is our principal? What's our P? 4,250. Our E is just E. What's our rate? Awesome. So we have to change this 5 to a decimal. So right now it's like 5.0. So we move it twice this way, so it becomes 0.05. So just remember, if it gives it to you in a percent, you have to change it to the decimal, so you move the decimal twice. And then what is our time? 10. So now we plug it all in. Our amount is equal to 4,250 times E to the power of 0.05 times 10. So what do we do first? Got to multiply that exponent together. So what's 0.05 times 10? 0.5. What do we do next?
You put in your calculator.
We got to put that E to the power of 0.5 in our calculator. So when I put in my calculator, I got 1.64872. Keep it in your calculator if you can, so you have all the decimals that come behind it. And we multiply that to 4,250. What'd you guys get?
7,007.0654.
So 0.65. The 5 would mean this rounds up to 7. So 0.07.